Donc, c'est une conférence co-organisée par le Centre d'études de la forêt et le Centre de recherche en matériaux renouvelables. Donc, aujourd'hui, jour pour jour, comme vous vous souvenez, jeudi passé, on a eu une conférence à Haïti, un terrain pour le partenariat universitaire en agriculture qui a été donné par le professeur Patrice Dion. Aujourd'hui, nous avons l'honneur et le privilège d'accueillir le professeur Nemkumar Banthia de l'Université de Colombie-Britannique pour nous parler un peu de l'Inde. Et moi, je dirais qu'au lieu de parler du terrain, c'est un terreau fertile. Un terreau fertile pour la science, l'innovation et la recherche. Donc, si vous voyez en Inde, vous pouvez alors remarquer comment ce pays excelle dans ces domaines-là de la science, de l'innovation, de la recherche. Donc, je pense que il y a, je le répète encore, un beau sol fertile pour le Canada, et le Québec aussi, de pouvoir collaborer avec ces pays-là. Comme vous pouvez le savoir, je crois, d'ici 2030, je crois que les deux grandes économies mondiales, ça va être la Chine et l'Inde. Donc, je crois qu'il y a une opportunité là de pouvoir travailler avec eux. Le professeur Banthia va nous parler évidemment de cette collaboration-là entre l'Inde et le Canada. Et il est le Canada. Et il est chief executive officer d'un réseau de centres. C'est le seul réseau d'ailleurs international qui est financé par le CRMR. Alors, je ne voudrais pas aller en détail de la carrière de professeur Banthia. Il a commencé un peu, il a d'abord fait ses études à IIT, Indian Institute of Technology de Delhi, et puis finalement il est venu à UBC, et en 87 jusqu'en 92, il a commencé sa carrière de recherche et de professeur ici à l'Université Laval avant d'être récupéré par l'Université de Colombie-Britannique, où il est professeur et chercheur distingué, comme vous avez pu le voir dans sa petite biographie. Professeur Banthia, c'est un scientifique de renommée internationale dans le domaine du béton. Et je suis content de voir qu'il y a des collègues de génie civil qui sont ici. Je crois qu'ils ont entendu parler de professeur Banthia dans la littérature. C'est l'un des professeurs ou des scientifiques qui est le plus cité dans ce domaine-là de sciences du béton. Et il est aussi titulaire donc, de la Chaire de recherche du Canada sur la réhabilitation et les infrastructures durables. Donc aujourd'hui, il va nous parler un peu de ces réseaux, des centres d'excellence et finalement la recherche dans son domaine d'expertise. Donc je vous souhaite encore une fois bienvenue à cette conférence. So, Nemi, thank you very much for coming to visit us. It's an honor to have you here as an invited speaker. Thank you.
Thank you very much, Demas, and bonjour à tout le monde. That introduction could have been a little bit shorter, but it's a real honor and a pleasure to be here, and I certainly am very happy to see some of my colleagues, previous colleagues from civil engineering here. So thank you so much for coming. When Demas asked me to talk about some of my work, I wasn't quite sure exactly how much of that would clearly interest you, but I said, well, I'm going to slice that in somewhere, I think, when I talk about my center with India. And it's been really a very exciting opportunity for me to launch this center with India. There was a competition back in 2012 for this Network of Centers of Excellence. As you know, the Network of Centers of Excellence program is old. Currently, there are about 18 centers that are operating. But this one is the only international center. And in order to launch a Network of Centers of Excellence, which is international, a very curious choice of a country was India. And I believe that that's an amazing, I would say, feat, I think, in terms of international relations, to choose India to work with. Now, India, as you know, is a country, one of the most populous democracy in the world, 1.3 billion people. And in 2030, India will be the second largest economy in the world, approaching almost close to $23 trillion in economic activity. China would still be number one at 40 trillion economy, and United States is expected to slide to a third place. So I think we are really at the right, moment in terms of working with a country that is transforming very, very rapidly. And I don't know how many of you have been to India, but clearly every time I go there, I think I see changes within months, how country is absolutely transforming. So it's a great opportunity for me, who was brought up in India, of course, is to work with the country and not only just give back to that country, but also to create linkages between my country of adoption, which is Canada, and also, sort of create these linkages with India. So, as I said, I see impacts. There will be a quiz afterwards. You have to tell me what IC impact stands for, but sorry, we won't do that. But it's a very large name, where S in the end stands for sustainability, and IC is India, Canada. The rest you can figure it out. The first and only international network of centers of excellence, pan-Canadian, pan-Indian, and equally funded by Canada and India. So we have approximately $30 funding from Canada, and we have $30 million funding from India. So it's a $60 million undertaking. And it's a nodal point for research to tackle problems in infrastructure, water, and public health. So those are the kinds of things we are doing at the moment. So these are the three core research areas: safe and sustainable infrastructure, integrated water management, and public health. So in the safe and sustainable infrastructure, which I lead, we are working towards low carbon materials, sensors for structural health monitoring of bridges and dams and civil infrastructure, and of course on strengthening. Integrated water management, we're very fortunate to have Professor Casa lead the integrated water management theme, which is again working towards sensors, alternative power supplies, and water treatment systems. And I'll show you some of the work we're doing in that. And finally, in public health, which is led by Professor Stuart Aitchison from University of Toronto. We're looking at rapid diagnostic devices, lab-on-chip sensors for rapid diagnostics, such as sensors that can quickly take a bodily fluid and detect if you have HIV antibodies in there, or any other antibody for that matter, particularly for water-borne diseases, and mobile health technology. So we're looking at solutions to problems that large Indian population. India, which is 1.3 billion people, has very close to 900 million cell phones. So you can imagine that, in order to provide the health services, India, the mobile health technologies could be very effective, where people can actually have solutions directly on their fingertips, know about, contamination in water, and find out and actually get the medical treatment directly from experts through mobile health technology. So those are the things. You will notice that, in fact, one of the running theme between these centers, between these different themes, is sensors. So there's a lot of work we're doing in sensor development, particularly for either monitoring infrastructure, monitoring water, both chemicals and pathogens in water, and finally, of course, lab-on-chip sensors, which actually detect through bodily fluids exactly what could be happening in our system with respect to diseases. So what we have done is we have launched 47 research projects so far. It's been about 6 years now. This has been 6th year, and we have another 3 more years to go for the center at the moment. And it's got 12 demonstration projects. I will talk a little bit about our demonstration projects, because the whole idea is not to just research and write a paper. The idea is to take these technologies to a community. And I'll show you how we are doing, taking these research findings and putting them into community, either in infrastructure or in water or in health. And those are the ones that we're very proud of, that we are actually transforming communities through our demonstration projects in the communities themselves. We have had 7 startup companies already, and this is where I think our economic development aspect comes in. The center has launched 7 startups. These are joint Canada-India startups, which is absolutely a wonderful thing to see, that our students are involved in entrepreneurial training, understanding intellectual property, and start their own companies. So the 17 technology deployments are infrastructure 5, health 2, and water 10. So I can see Professor Casa's team is very, very active. So thank you, Professor Casa, for really leading that. We've had 27 patents already. The center has launched 27 patents and invention disclosures. We have had 800 HQP already. These are joint HQP. So there are 800 PhD students in the program. We have published over 808 journal papers that have come out of the center already, and 290 partnerships. There are approximately 170 professors involved in the center right now on both sides, and these are collaborative projects that we are working on, which is really something we are very, very proud of. Of course, these are our partners and collaborators. You'll notice some of the large companies, StarMos, for example, Tata Consulting Services, Xerox, GE, which is a very big part of our work with water at the moment, which is funding quite a bit of work. GMR, that's a very large, is one of the largest companies managing airports at the moment. 6 of the largest airports in the world are managed by them right now. BI Pure, SFU, of course, NSERC Funset. So there's a very large network of about 260 collaborators that are part of the center right now. Now let me show you, I know research you can always read about, and when we fund research, we are funding generally at a very high TRL. I don't know if you know about the TRL levels for research. These are technology readiness levels. So we don't fund fundamental work. We only fund research which requires additional adaptation towards prototyping. So, for example, if you had an idea which actually wouldn't, you think, within the 3 years or so, could actually be deployed into a community in the form of a prototype, those are the kinds of research projects we are keen on. So we don't do fundamental, pie in the sky, blue sky research. We are more into applied TRL 6 and above research. So I'll show you some of the work that we have done. Here's a road that we built in southern India, which is just 2 hours from Bangalore. It's a concrete with nanomodified hydrophilic fibers, some of the work that I do in, and it's a self-healing road. So this was actually cast in 2013. This was done in June, and India is very hot in June, so this road cracked up. And within 2 weeks, in fact, all the cracks had actually closed. So this is an example of a self-healing road. India needs, get this, 2.3 million kilometers of roads right now. And clearly, when you have these rural roads, these are the ones that actually are the ones to be utilized. This actually costs less as a first-time cost, and it's expected to cost at least 3 times more than their normal roads do. So this is one example which was done with a number of companies, both Canada and India, which allowed us to actually, change the community. And just as a social impact, this community of about 1,400 people, they didn't have a road. So when we built this road, the per capita income of the village moved up by 20% in 1 year. And that's exactly the transformation I'm talking about, that a community which does not have infrastructure, you bring in a simple infrastructure. Now they're able to take their produce out of the city, to the city. They are now connected to a much larger network where they can actually trade their milk, their corn. Innovation has started, rehabilitation has started in the town itself. So I think, this is how I think communities transform. And I think, if I could just plug in for civil engineering, I think the civil engineers have, through an infrastructure, greatest opportunity to transform communities, much more than, I would say, in other disciplines. There's another project we had where we are strengthening schools against earthquakes. So this is a technique developed in my laboratory again, which we are calling EDCC, which is eco-friendly ductile cementitious composite, which is a highly strained and absorbing or very high strain capacity concrete, which gets up to say 4 to 5% strain. And we're using that to strengthen schools against earthquake. As you know, BC gets about 2,500 earthquakes. I mean, of course, yours is also a highly seismic area that you live in. So we have a big problem with the major one coming. So we have about over 400 schools in BC that require seismic strengthening, where small children are. So we need to strengthen these buildings, and we developed this very cost-effective method. And we've already done one school as part of my center, which is the Jamieson Elementary School, and we strengthened it. And the entire strengthening took place just over 2 days. So we were in there with our spray guns, And we actually sprayed this. Mark, you will like this particularly in terms of it's a sprayed EDCC that we actually placed on these unreinforced masonry walls. And then, so there's another project coming up in India now. It's a girls' school in Roorkee. So I'm just giving you an example of how research gets translated into making an actual difference. There's a project within infrastructure. We have a scour monitoring. This is done by Professor Azari from University of Toronto. Azari did her PhD with me, so she's now at University of Toronto. I don't know how many of you know this, but the scour of bridges is a very large problem. So if we looked at BC bridges, about 60% of them showing scour. Scour is when you increase the water flow, you end up losing part of the foundation. And if you'll recall that this particular bridge that collapsed in Minnesota, which was also in fact a scour-related problem where the piers had actually turned. So here's a sample sensor that we are monitoring right at the foundation level, which will give indication when we have scour in the foundation itself. This is a dissolved oxygen sensor, which can give us a quick signal that yes, the bridge has lost its foundation and something needs to be done at the moment. So we're looking at these kinds of sensors which can do a lot more work. Now, in the demonstration projects in the water, there is a water treatment project in Lytton First Nations community. There's Professor Majid Mohseni from University of British Columbia. As you know, in a number of these First Nations and Aboriginal communities, there is a boil water advisory. They cannot drink the water directly from the tap. So what we are doing is we are looking at methods frugal methods, cheaper methods, of doing water treatment. So this particular method, electrocoagulation that Professor Majid Mohseni is working on, this was the first time installed in the Lytton First Nations as part of our center's work. And after 18 years, the boil water advisory from this community was lifted, which is great that the people can now drink the water directly from the tap in this particular community. And I think that I see as a real impact, I think, of some, the work that we can do. It's a simple work, but certainly very useful, I think, for transforming communities. There's the water project, again, using passive membrane. And this is one which has been utilized in West Vancouver now at the moment, which is, again, a passive membrane process where we are looking at utilizing this membrane for water treatment. And we are looking at similar processes now. Here's a project that Professor Casa is leading from Laval, which is testing and upscaling phytoremediation technology in real-world conditions. Again, this is another very exciting project. We are looking at water health nexus, I think, in order to essentially clean the water through natural methods. And I think perhaps Professor Casa can talk a little bit about it, perhaps when you have a minute. On the health side, we're looking at a number of health projects now. One is a smart app-based rapid multiplexing screening of HIV. This is a project which is being demonstrated right now. It's a lab-on-chip concept where you can get an HIV detection within a short period of time. It takes basically minutes. Again, normally the HIV test would take up to 3 days in India to get your results back. Here we have a method which can give you the results, a digital readout within minutes, actually, which is wonderful, I think, in a country where HIV is growing very rapidly. And then there's a dial-in, which is we are looking at vaccinations. So this is a project which is now partly funded by the Gates Foundation. We're looking at vaccinations. As you know, Bill Gates has actually started major operations in vaccination. So this is a project where we have set up a hotline which explains to people when the child is born what kind of immunization the child needs. And then there is effort actually made by people who actually run this hotline to explain to people in the villages that these are the vaccinations that you need to take and provide that support for taking the child over to a vaccination center. So this is one of the very exciting, I think, projects with Professor Jory, which is at University of Montreal. So in terms of really where we're going with the project, of course, the demonstration projects, I just gave you a very brief overview of what we're doing. But there are new projects. Please look up our next call for proposals if you're interested in actually setting up a collaborative project with your Indian partners. These are joint proposals, as you know. Here we have just launched an IC Impacts and DST, Department of Science and Technology project in India, which is on fire, building fires. So we are looking at improving occupant survivability in fires. India has the highest burden of fire deaths. 25,000 people die in building fires every year. And what we're doing as part of this particular center is that we are developing not only the material science side of things, that these are fire retardants, better improvements in structural designs, for example, but also using its cyber-physical interfaces, which means that if you had sensors, you could actually be calling the fire hall directly, that the sensor would make a call as opposed to people have to make a call once they notice a fire. So these are the kind of cyber-physical interfaces which we are developing in terms of the projects itself, that so that you would minimize, those deaths related to fire. So for example, this is an example I always quote. Remember those World Trade Center fires in 2001 in New York? If that building had sensors, if that particular building had sensors, you would be able to do a collapse analysis very quickly based on sensor data, and you would not send those 400 firefighters up. This is possible these days, I think, to do proper sensor modulations and sensor data acquisition, that you would know how much time a specific girder or beam or a floor has there to survive. So I think this is another very interesting project that we just launched, 4 projects in that area. We are looking at essentially projects in the First Nations, particularly on the housing side. As you know, the First Nations housing is in a very bad shape. So we are looking at mold-resistant clays, mold-resistant nanoproducts. We are looking at other methods. And of course, with the climate change, this is what is changing up in the north. A lot of the permafrost is going away, which means that the foundations have a much larger problem in these First Nations communities. So we're looking at really methods of somehow bringing new technologies into creating housing for First Nations, which can then be resistant, it can be sustainable, and it would be, of course, frugal and low cost. We also have a new public health project that's coming up with spinal cord injuries. As you know, Vancouver also hosts the Rick Hansen Foundation. I don't know how many of you are aware of the Rick Hansen Foundation. Mr. Rick Hansen actually went around the world. If we may recall, he was called the Man in Motion, and he actually generated over $100 million for spinal cord injury. He actually had a spinal cord injury himself in an accident. So he generated about $100 million for spinal cord research. India also has the largest number of tetraplegic and paraplegic in the world. And what we are doing is we're developing wearables, we're developing IoT-based solutions, and cheaper wheelchairs, which can actually be working to make the lives of these people with tetraplegia a little bit better. So we just launched these 5 projects, which are on IoT-based devices and lighter materials, etc., which could be utilized for improving the lives of these people, particularly using, again, cyber-physical interfaces. So we just launched these number of projects to improve the lives of people with spinal cord injuries. Looking forward now, we just had wonderful meetings with the senior administration here at Laval. We invite Laval to be a part of the center. Of course, Professor Casa is doing a wonderful job as the team lead, but we also have the opportunity to bring Laval as an affiliate partner. And I think if we were to, certainly, would be very happy and proud to have Laval University as an affiliate partner with the university itself. But that doesn't stop you from applying for funding directly to the center. If you have a project in mind, we'd be happy to look at, particularly demonstration projects. So Benoit is here as well. Benoit, there's opportunities to put some of the new technologies you're working through CRIB, perhaps into an Indian community. And there are funds available for those kinds of things as well, actually. So please do consider that. Next stop is China. We just had wonderful meetings in China. We are looking at expanding the center to China now, which with TUS Spark and certainly with Ministry of Science and Technology there, we're looking at expanding the center to China. And I think it's a great model, that we could sort of certainly look at. How am I doing time-wise? Another 15 minutes? Okay, all right. So this sort of, concludes my talk on the center itself. I understand there are people from sort of forestry and biomaterial side here. So I'm going to talk a little bit about some of the work we're doing in the laboratory, in my laboratory on cellulose, particularly reinforcing concrete. But maybe I can stop for a few minutes. There are any questions on the center itself? I'd be happy to answer those before I go into some of my own personal research. Yes, please.
They come from public institutions, like some from the government, for example, and also from private institutions, or it's only for private?
So we have a nice 60-40 split. So 60% of the funding comes from the government, 40 comes from private corporations and societies, and of course, not for profit. But 60% comes from the government.
Do you see that the government itself from Canada and India, they do put a lot of effort to make these things happen, or?
Yes.
Yes.
Yes, you need government support in these projects always, and you also need community support. But one thing I learned early on was that no community will let you come in and demonstrate technologies until they trust you. You're always seen as an outsider, and they always see that you have some kind of ulterior motive, I think, behind using your technology in a community. So you have to build that trust. So this little village I was talking about in Tarnivavi, or the Lytton First Nations, it takes a long time until you build the trust with the community that will allow you to demonstrate your technology there, right? So we are very thankful to communities for letting us in. Yes, please.
Do you provide a mechanism to interact with other Indian institutions? You're talking about our Indian partners that we don't have any at this point. Is there a mechanism to network with?
Absolutely. Absolutely. Professor Casa is the right person to talk to. And our team leads are the right people to talk to. So if you do identify a specific institution through internet, for example, that are doing excellent work in your field, and you think the complementarity is there with that institution and what you would like to do, certainly those contacts can be very easily made. Every time we launch a call, we often have a workshop, either here or in India, and you're always welcome to attend those. Yes, Benoit.
D'autres questions? Oui.
Are there some initiatives maybe to promote internship, back and forth from India to Canada and the integration as well? Students, personnel,
Yes, great question. So currently, there are funds set aside for mobility in the program, and number of students go back and forth in a project. So if you have a joint project with India, then this becomes a wonderful context for students to go back and forth. Because, when the students just go, if you look at the MyTex program, for example, so the students go to an institution, but there is no overarching project there. They just show up in the lab, and I have a bunch of them show up in my lab and say, what am I supposed to do next? This one is much better because you already have an ongoing project with that institution. So if your student goes there, he has a real purpose, in going there. And one other thing I would say is we also have funds available for students to organize leadership events. So we give $15,000 to students to organize a workshop, for example. So if you think that you want to, work with India, the students particularly, you can actually avail funds from the center to organize a workshop so that you can talk to people that you probably otherwise would not talk to. You can have, invited speakers to that meeting. You can build that kind of linkages with Indian institutions and then perhaps create another mobility route. Vous parlez français aussi, probably. Yes, please.
I want to know, based on what elements you define the projects, because, for example, are there some indicators that lead you to define the projects, or it's randomly?
No, it's not random. We are in the three disciplines, or three, I would say, themes of or sectors of infrastructure, water, and health. And if the project is within that realm of broader, health, infrastructure, water themes, we certainly are happy with those.
From past, and you define the projects on the pre-existing problems?
Right. So there are two countries involved, don't forget here. So I think these areas are identified by both countries as the areas of collaboration. Energy is something that we are adding more from water treatment side. With India, number of communities are off-grid. So we are also looking at energy or renewable energy, particularly from water treatment side. But as long as it falls within the general realm of infrastructure, water, and health, which are the needs of both countries, we will be happy to launch those. And don't forget, there's another country involved here, which means that we do need funding from them to launch these calls. So it's dollar for dollar support, basically, that we require for these projects. So they fund the Indian counterparts, we fund the Canadian counterparts. Okay? All right, thank you. So I'm going to take another 15 minutes or 10 minutes of your time to talk a little bit about biomimicked multifunctional fibers for ultra-high performance fiber-reinforced concrete. So I work in fiber-reinforced concrete, and I'm trying to interface that now with more cellulose biomimicked or bio-inspired fibers that we are now using. Or you also see have a wonderful center here on biomaterials or renewable materials, which is great. So we're looking at those in concrete. I don't know if you've noticed this, but there's a huge issue with deterioration of structures everywhere in the world, and you're always looking for new, better materials that can help us truly rehabilitate, build new structures which actually have much greater longevity. And if you look at actually our material application, you will somehow notice that our lifespan of our new materials we're using is getting shorter and shorter. So we may actually be talking about, in fact, wonderful innovations, but the structures that we build today are actually lasting shorter. And if you look at now the structures that are built, this is Statistics Canada number, they're only lasting 37 years, whereas we pretend that we are designing these structures for 100 years. And I think problem is really in different types of materials that we're using, and the corrosion and the de-icing salts and those kinds of things that you're sort of placing in these on these structures. So FRC, fiber-reinforced concrete, where you take the concrete and you add fiber to it. So you will notice that here there is this kind of concrete that we place. This is the concrete which we spray, and we can add these fibers of different types of materials. And I will talk a little bit about the cellulose particularly that we're using in order to produce concrete which has got much better characteristics. But the fiber, concrete with fibers would look something like this. And what you'll notice is that fibers now become the wonderful bridges. So if you have a concrete which will crack, basically we are looking at fibers. These could be cellulose, which is actually now bridging a crack. And the moment the crack bridging takes place, you don't allow these deleterious agents to go inside the body of concrete, and then that actually makes the concrete much more durable. We are also looking at much greater strain capacity. So, some of you probably understand the steel. Steel has a elastoplastic response. What we are looking at in these systems is a typical EDCC, where you can get up to, say, 4 to 5% strain in the material itself. So not only you're making them durable, we are also making them basically much more energy absorbing or much tougher as we get more, which has got a much greater fracture toughness. So I don't know if you kind of follow the fracture mechanics. We're looking at basically much greater R curve, or you're looking at much better G sub C values. It means it'll absorb much greater energy before it collapses or before it fractures. Now, it's a very advanced field. I mean, it's a very highly developed area. You have applications. This is the John F. Kennedy Airport in New York. It's another one, which is industrial floor, all made with fiber-reinforced concrete, permanent formwork, sort of wave breakers, precast products. This is a project in Iraq. This is the Al-Shahid Monument. This is all carbon fiber reinforced, so the same concrete, but with carbon fiber inside. So it's carbon fiber reinforced material. We built a number of bridges in this country using fiber reinforced concrete, which is what we call steel-free decks. So these are the ones which have no steel, but basically just fiber reinforcement in them. These are the St. Lucas Hospital in Tokyo Bay, all these carbon fiber reinforced panels for refractories. We're using a lot of fibers there. On the shotcrete side, a lot of work on canal lining. I know Laval is a big center in doing shotcrete research here. Rehabilitation of transmission towers, fire damage, bridge pier, and seismic retrofit. So there are a number of these applications that we're doing. Now, off late, what we're doing is, this could be your fiber-reinforced concrete of the past. What we're doing is now we are actually trying to increase the performance of this material by increasing the strength. So you'll have this kind of ultra-high performance concrete where you're increasing the strength of this material, almost going up to a strength of 250 megapascal. Your normal concrete would have a strength of, say, 40 MPa, 40 megapascals. We're looking at these high-performance systems with extremely high strength and extremely high ductility. So here it would be your normal fiber-reinforced concrete that I showed you, and here is the material which is what we call ultra-high performance concrete, which is up to, say, 2% fiber. And you can see that compared to this, we are having a much, much better response, which has got a number of applications, which is good for repair, good for seismic applications, good for blast and impact, good for girders, good for bridge decks. So a number of these applications have come about using ultra-high performance concrete. One of the problems with this material is it also has very high autogenous shrinkage. Now, concrete shrinks, as you know, and these ultra-high performance materials, which have very low water-cement ratio, they end up having very high probability of cracking, which is either we call chemical-induced shrinkage or autogenous shrinkage. And if you have this particular problem, which comes from self-desiccation. So concrete, because already in order to increase the strength, you have reduced the water content, what you end up having is basically a material which has a much greater desiccation, much greater reduction in relative humidity inside. And the moment there is a drop in the humidity, you end up having cracking in the system because the material is actually now trying to shrink. So this is a very large problem with ultra-high performance concrete. So what we're looking at is the new types of fibers. And that's where I think cellulose becomes, in fact, a very good material because cellulose absorbs water. So if I used cellulose as a material of reinforcement in this ultra-high performance concrete, we can actually have a material which is crack-free. So this concept is called internal curing. So you bring in the water, concrete requires water for hydration. If you don't have, if you have self-desiccation, it will crack, and it would also not allow that hydration to take place. So hence we bring in this cellulose product, which actually brings in additional water into the body of concrete, which allows additional hydration, and it also combats internal shrinkage. So you get crack-free material basically using cellulose. So here is your typical material. This is kind of the composition for ultra-high performance concrete. You can develop very high fluidity, so it will be self-compacting. But unfortunately, the fibers we are using these materials are borrowed from other fields. So we still use fibers that the aerospace uses or fibers that are used by automotive side. We really don't have fibers that are designed for concrete itself. So here is a project I want to define where we're looking at engineered fibers for your ultra-high performance concrete, which does not show any signs of, and if I can get very high strengths, you're looking at almost 10 times more compressive strength, almost 15 times more flexural strength, and this could in fact become a wonderful material. So I just want to very briefly talk about these bio-inspired surface-exalted cellulose that we are developing for internal curing as part of my work with the center itself. Now, good thing about cellulose, of course it absorbs a great deal of water. So you have basically This is the water absorption. You can say up to 25% absorption in the system itself. The water resides somewhere in the system which is available for hydration. And what happens is, here's your water retention. You kind of get this very high, quick water absorption. But what is also critical is that the moment you lower the relative humidity, that water is actually desorbed very quickly. What that means is you lose that water very quickly the moment the relative humidity drops. And I like that because I want that water to be released very quickly back to the concrete when actually there is desiccation, and I need that water back into the system as quickly as the relative humidity drops in the body of concrete. So cellulose is a wonderful material for internal curing of this particular nature. But we went one step further. We said, oh, wait a second, we can fibrillate cellulose even more. So we start off with recycled cellulose, which is essentially a byproduct of the pulp industry or paper industry. We send it out to a mechanical pulping unit where we can actually fibrillate this cellulose even further. So we are doing essentially a fibrillation of the cellulose. And when I get this cellulose which is fibrillated, I centrifuge it, and I get a material which has got even a greater water absorption capacity because of the fibrillation. I have a much greater surface area, and now I can get, in fact, a much better response to water absorption, and it will continue to desolve, which will continue to give out that water when I need it, which is a wonderful way to do it. So here is our typical fiber. Here's your water retention value. You're going up to, say, 160. And here are the products that we have actually fibrillated. So here is your unfibrillated. Here is the one which is fibrillated 100 kilowatt hour per ton. Here is the fiber or pulp which is fibrillated at 185 kilowatt hour per ton, which means that you can see that now from 25 fibrillation percent absorption, what I can do is I can go up to 160% absorption, and I have lots of water now in the system to be given back to concrete when the need arises. And I think this is the real principle of internal curing. Now, there is a great deal of work going on nanocellulose. Of course, there's the nanocellulose, nanofibrils, and nanocrystals, which are being utilized. So these are some of the nanomaterials that we are using. These are highly fibrillated. They are very highly fibrillated. And if you look at basically the energy absorption in this nanofibrillation, you will notice that it almost takes up to 5,000 kilowatt hour per ton for producing these nanofibrils and nanocrystals. Our material is down here, which is quite interesting because our energy absorption is of the order of only 100 kilowatt hour. And I believe that's required for sustainability because you don't want to use too much energy, I think, in order to produce the product, which is cost and also energy requirement. And I'll show you that this particular material with optimized energy is a better material than one which has got almost 5,000 kilowatt hour of energy imparted to it in terms of concrete performance. You don't really need that level of microfibrillation or nanofibrillation requirement here. One other material which we use is superabsorbent polymers for internal curing. Problem with superabsorbent polymer is that, of course, it absorbs more water than cellulose because this is a superabsorbent polymer, but it also leaves a void behind. And because it leaves a void behind when there is actually water actually extracted from superabsorbent polymer in the body of concrete, you end up having a loss of strength. Cellulose doesn't do that because it's not actually creating a void as a result of its water extraction process. And I'll show you that, in fact, you don't get that kind of loss of content or loss of strength as a result of the desorption in the cellulose itself. So let's just take a look at what we have done, with the cellulose, which is fibrillated cellulose into concrete itself. So I'm going to show you a couple of tests. One is actually a thermoporometry, and I'm sure some of you have already used thermoporometry before, where you're looking at actually freezing the system. And when you freeze the system, if there is a pore refinement, you would get more supercooling because the water in that supercooled pores is under absorption. So it actually shows more supercooling in the system itself. So in thermoporometry, what we do is we would actually freeze the system, and greater the depression in the freezing point, I know there has been a reduction in the pore diameter, which is what we call pore refinement. And I like that because smaller the average pores or pore diameter, more resistant the material is to ingress of deleterious agents, right? So I want this to be a non-permeable system which doesn't allow any deleterious agents to go through. And what you will notice is very interesting. Here's the mercury intrusion porosimetry tests, and these are our thermoporometry tests. What we're doing through fibrillation, here is your 0%, 1%, and 0.3% of the cellulose that we are adding. What you will notice is that actually I'm converting quite a bit of the microporosity in concrete, which permeates. You know, water can permeate through microporosity, but it does not permeate through nanoporosity. So under 50 nanometers, concrete will not permeate. And what I'm doing through this surface exalted cellulose is I'm actually converting microporosity into nanoporosity. And that's very exciting because what I'm doing here is I'm making concrete far more impermeable. Now through some tomography scans here, we're looking at these sort of dual scan tomographies with Xylon. And you will notice that in fact, when you look at systems which have got cellulose in it, here's a sort of tomography scans. Here's your one without cellulose, and here is your one with cellulose. And you can see that I'm also reducing the total porosity, and at the same time, I'm also reducing the water absorption, which means that you are actually coming up with small amount of fibrillation in this system, which is becoming a lot more impermeable, and it is increasing very much, or reducing the porosity and increasing the strength as well at the same time. Now, one typical test we do is called autogenous shrinkage. Remember, that's why I started. The concrete is going to shrink because of the low water-cement ratio. And here are some sort of autogenous shrinkage tests here. Here is your autogenous shrinkage with our material. This is 100 kilowatt hours. This is a 0 kilowatt hour. And there is 185 kilowatt hour. You will notice very quickly that at 185 kilowatt hour, when I have given more energy in fibrillation, the results don't look as good. It means it's actually shrinking more. And if you look at this 100 kilowatt hour, what you're noticing, that seems to be the optimal fibrillation that you require, and there's no need to spend more energy in producing this product, which has got greater fibrillation than what we absolutely need. And if you look at now those 5,000 kilowatt hour nanomaterials that I was talking about, you will notice that its performance is either similar or worse than some of our fibrillated material, which that means is you really do not require the nanofibrillation for the purpose of actually providing internal curing. Some other data here. This is permeability when we are actually forcing water through a body of concrete. You'll notice that, in fact, we are looking at similar systems here where you have a cellulose which is actually maintaining its impermeability. This is stress plotted as a function of permeability. You'll notice that without the fiber, you get a little bit of pore depression or compression, and then you will get a plain fiber which cracks up, and you'll end up having a much greater increase in permeability. And in our cellulose, you'll notice that there is still pore compression under stress, but then you don't get much greater increase in permeability because of that conversion from nano to micro porosity that we are talking about. Cellulose is also a binding material. It binds chlorides, the ones that come through your de-icing salts. And here we have a very clear indication that your actual diffusion coefficients are actually less through a cellulose modified system. And finally, the proof of the pudding is always in corrosion control, because that's what first slide I showed you, is that our structures are corroding. All the rebar in our structures is corroding. So if you look at these systems, with our cellulose, we ran some tests here. Here's the loaded beam, which is in a highly aggressive, highly corrosive, highly chloride-laden environment. So we are causing this to corrode, this particular rebar, which is in this particular setup, and we are monitoring basically the corrosion activity through a number of methods, linear polarization, half cell, and those kinds of things. And what we notice, which is really the proof of the pudding, as I call it, it's the time to corrosion in terms of weeks. And of course, these are accelerated tests. You will notice that this is no loading, and you'll see that this is at different levels of cellulose. You'll notice that there's no loading. Our cellulose at 0.3% is absolutely delaying the corrosion quite significantly. When I have some loading on the beam, I see a less of a reduction in overall sort of delay, but still there is a delay as compared to the plain system. And when I exceed the load beyond a certain point, the cracks have opened far beyond, and I will not see a benefit of cellulose internal curing at that point. But most of our designs standards will allow a load of this particular nature only, which means for existing structures out there, there will always be a method of improving the durability for structures through our surface exalted cellulose. This brings me to the end of the talk. I'd be happy to answer any questions, but I thought I'll just bring in something on the sort of the bio-inspired and biomimic side and how we are interfacing in civil engineering in that particular topic. Thank you very much.
On peut poser les questions en français.
Yes, please.
You said that when your fibers dehydrate, they stay in place, but like we know that wood, if we left it in the forest, it would rot away. What happens to the cellulose? It never composts in the structure, or it?
Interesting. Cellulose is much better than wood because there's no lignin on it. So it definitely helps. The lignin is not a good material for us because it retards setting. So these cellulose fibers actually don't have any lignin on it. And some of these cellulose that we're working in also have some kind of permeable polymer coating on it. So we're looking at coatings as well. But so far, it's a very good question. So far, we haven't seen any deterioration after 2 years in some of these specimens yet. So the key may be to have pure cellulose to work with rather than wood. Yes. Yeah. Well, we don't like lignin because lignin is a retarder in our system. It doesn't allow setting. It's a set retardant actually in concrete.
So in one of your slides, you show different sources of cellulose, including alpaca. I used to work with alpaca from Alberta.
Uh-huh.
And did you have different response depending on the source of your cellulose?
No, we did not actually look at different sources. This was all supplied by CAN4. CAN4?
Oh, CAN4,
yeah.
But one of your slides I saw alpaca.
That's a comparative research, actually, we were comparing to, actually.
Have you checked the reaction of this cellulose made concrete in the presence of any admixtures in the concrete?
Yes. Yes, they all have admixtures in concrete.
What type of admixtures?
But they have both superplasticizer and air entraining agents.
So there were no interventions in the properties of the concrete?
We didn't see that, no. But don't forget, it's a very small amount of fiber. You're looking at 0.1 to 0.3%. It's a very tiny amount of fiber. And the fiber is not doing anything mechanically. What it's doing is at the internal pore structure only. We're providing internal curing where it's needed. So it's very engineered in that sense. Yeah.
The cost of this new concrete is somehow much lower than the regular one, or is it the same?
So first-time cost is different from life cycle cost, right? So the first-time cost is, of course, higher. When you're adding anything to concrete, it's going to add more cost to it. So in this case, because cellulose is a very cheap material and we're using recycled cellulose, it's adding perhaps less than 6% to the cost. So, if your concrete is, say, $100 per meter cube, I don't know what your cost in Quebec is, but about $100 per meter cube, you're looking at about $106 per meter cube with cellulose in it, at 0.3%. But I think that's misleading. I think we should not look at first-time cost. Look at those structures that are deteriorating. So if you can increase the lifespan of a structure through these, internally cured systems, that is a much bigger value to society for me than this first-time cost increases. Imagine if you had in Quebec, I know Benoit, correct me if I'm wrong, if you have, say, 15,000 bridges in Quebec, something like that, more or less. So if you could increase the lifespan of each and every of those 15,000 bridges by 10 years, imagine the cost savings there. Huge. I think Benoit had a question.
Very interesting talk.
Thank you.
I'd like. Do you see some benefits in? You've been presenting the use of these fibers in ultra-high performance materials. Do you see any benefits, advantages to extend the use of these fibers to a variety of other type of concrete?
Absolutely, I think so. If you're able to somehow, I would hybridize these fibers because these are essentially designed for ultra-high strength systems where autogenous shrinkage is a real problem and you need internal curing. So I would actually do two things. One, for those concretes where curing is not possible, shotcrete, for example, has very large problems with curing, and in general, curing doesn't take place in some situations. So there, not as an excuse for not curing, but it could actually provide a much better, I would say, material integrity somehow if curing was to be missed, which does happen. The second thing I would say is I think for normal strength material where there's proper curing, I would hybridize this with other existing fiber products, which would allow you to have benefits of pore refinement as well as toughness at the same time.
Est-ce qu'il y a d'autres questions? Une dernière ou deux? Bien, je crois que...
One last question. How persistent is cellulose in the environment once you become, like if you look at the full cycle of your product when it's actually being decommissioned, does it actually stay in the environment or will it eventually?
Cellulose?
Yeah.
That's a good question, but I mean, cellulose is a natural product, so I'm not particularly concerned about it being in a decommissioned building.
Okay.
It's not asbestos, so.
Yeah, can you recycle your product afterwards and it's not
Oh,
going
that's
to
a
have
very,
health effects?
that's a very different question, though. I think, if you can actually recycle, concrete and, can you take a decommissioned girder or bridge column and then crush it up and actually put it back into new concrete? And I don't particularly see any problem, but I don't think we are quite there yet with our research. Okay? Sorry, I took longer than I was going to, but thank you for your time.
Thank you so much, Dr. Banthia, for coming and talk to us about IC impact and your research work.
Pleasure.
So really appreciate it. So, we don't need to...
Thank you. Thank you.
I know that